Good, then let's continue. So the aim for the next hour then is to first introduce the model that we are actually going to deal with the whole winter term, namely the general linear model, and basically trying to take you from where you stopped, or you stopped in undergrad statistics, and trying to make the connection to what we are doing now, then use this as a motivation to start looking into some very essential mathematical foundations that we will need all over the course, and you need all over data analysis. Yeah. So the content of the winter term serves, I think it serves three purposes at least. So the one purpose is that you learn about the general linear model, because it's the foundation of everything that is done in cognitive neuroscience fMRI data analysis. Another aspect is that the GLM is kind of a fundamental thing in classical statistics, so that you basically revise your classical statistics. That's the second aim. And the third aim is that you become familiar with formal approaches to data analysis, because that's what you will if you continue in cognitive neuroscience, that's something a very essential skill, and something you will do all the time. Okay, so maybe let's start with the question of, in your statistics undergraduate course, who covered the general linear model? So who talked about the general linear model in your statistics course? So that's in Osnabrück, and you studied, what did you? And what kind of course? In psychology? Yeah. Okay, cool. So Canadian statistical courses are better than German courses, as we just figured out, because they talk about the general linear model, and German or other countries, which are all represented here, don't. Good. So if you talked about the GLM, what is the GLM? That's okay. Maybe the Canadian courses are not that good, because so what is the GLM?
It's a linear model that follows the equation of y equals x plus b. And that's about it.
Okay. And in Osnabrück, what did you learn about the?
So we had x and y. So we have one variable that is predicted as a variable y. We have this like basic equation which we can extend with different parameters, and
okay. And so that's kind of the mathematical description of it. But do you have something else on your mind if you think about?
I just have this intuitive picture of a line that we can fit to data. And,
okay. Okay.
we have the error term, of course, which is important for the certainty of estimation.
Okay, let me stop you there. That's all true. One thing that you should, although the line in terms of simple linear regression is an important thing, but so the intuition that you should let go of now is that the GLM describes a line, because we will use it in very different settings, so it not always describes a line. It can describe a line. Okay, anyone else who knows what the GLM is or has a perspective on it?
So in high school you learn this simple linear model, right? X is m times b plus c or whatever. And this is a generalization to matrices. So it's not about just scalars anymore, but now it's S and matrices, but it still has the same form.
Yep. So I will tend to repeat your answers. Don't feel weird about it. I'm just doing it because I don't know how good the mic is, so that it's not completely weird when one sees that. So basically the answer here was that it has to do with matrices, and it's a generalization of the simple linear regression model to basically more dimensions, let's say, and it uses matrices. That's all correct. So the Yeah, anyone missing? Somebody who wants to? No. Okay, so the way we everything that you said was perfectly fine. The way I will present the GLM here is as kind of the mathematical unifying perspective on most of the techniques that you learned about in undergraduate statistics. So what I'm trying to, so this is also kind of one of the, like I said, one of the purposes of the course, so that you revise your statistics. And the perspective that will be offered is that the GLM is a generalization of things that you know. So for example, simple linear regression. Who has learned about simple linear regression? That's only half. What happened to the statistics courses? The easiest generalization of simple linear regression is, of course, multiple linear regression. Who learned about multiple linear regression? Oh, that's a lot of you. So in undergraduate statistics at FU, did anyone study at FU actually? Nobody studied at FU. Undergraduate statistics in Germany. Did you not study multiple linear regression?
I kind of know what it is, but we did not apply it.
Okay, but you learned about it.
Yeah, I
Okay.
understand it.
You know the term. Good. Good, because that's usually what is covered. So multiple linear regression, this is already kind of the way that the GLM is applied to fMRI data, and in a way you can also think of it as the most general form of the general linear model. But there are a number of statistical techniques that you will also have heard of, which are also can be conceived as special cases of the general linear model, namely t-tests. So who has learned about t-tests? That's a lot of you. So what kind of t-tests have you learned about? So you, what's your name? Sorry, I have to learn the names. No, you. Yeah. No, you with the long blonde hair. Nede. So what kind of t-tests are there? Yeah, and what are they called? Okay, then you're also called Nele, aren't you? No. What's your name?
Annika.
Annika. Okay.
I don't know in English, but like connected or unconnected groups?
Okay. So there's something called dependent, independent, yeah, but this is already a subcategorization of something else. So how many samples do you need to have them to be independent or dependent? Is one sample enough? No. So you have to have two. So there are things called one sample t-test. One sample, and there's something called two sample t-test. And there you can have dependent and independent. And independent, but you can only have these independent, dependent if you have two sample t-tests. Okay, then what is the generalization of t-tests to more than two groups? What's that called? Yeah, so that's the analysis of variance. What types of Anova have you heard of? Maybe someone else? One-way Anova, exactly. So there's something called one-way Anova. One-way Anova. And if there's one way, there's also more than one way. So let's call that n-way Anova. Because there's two-way, three-way, whatever Anova. And then I assume you, when you talked about Anova, you also talked about interactions. Who has heard the term interaction? Okay, that's a couple. Because you can have these Anova types with or without interactions, but usually they're taught always with interaction. Interaction. Good. What are we missing in terms of the GLM? Who has heard about Anova? Okay, that's all basically the same people. So Anova, that's also a specific case of the GLM, so analysis of covariance, and we will actually get to that. Maybe if you are now also starting to read fMRI papers, just as a first tip, secret tip number one. So Anova in the fMRI field, that's known as PPI, especially if you're fMRI data analysis. So once you come across a PPI paper, that's actually Anova, so you can relax. But we will talk about that in detail later. Okay, let me check whether I forgot something that we will discuss. Maybe let's also look at the intro. One sample, independent, classical, multifactorial designs. Yeah. Okay, yeah. So basically all these things, Anova, Anova, t-test, multiple linear regression, and simple linear regression, and their different forms, things like repeated measures, Anova, and so on. They are all basically special cases of the general linear model. So this is why when I learned about the general linear model, after learning about all these specific cases, that was really helpful, because I had the feeling there were all these different statistics techniques, and somehow they sometimes felt similar, but not really, and it was not really clear how they are related. And this is kind of the viewpoint that I offer in the statistical methods class, that the general linear model is a unifying perspective on these techniques. And as we heard, also there are linear models. It also so linear models also play a role when they are not basically related to classical statistics. So, for example, who has heard about logistic regression? That's very few. So in the statistics classes, maybe not. But logistic regression also has kind of the linear model in it, but then works a little bit different. So the good thing with linear things is that you then can always extend them to nonlinear things. And once you understood the linear case, the extension to nonlinear things is relatively straightforward. So it also, although formally, it's not correct to say that logistic regression is a special case of the general linear model. It's very, very much related. And also things like neural networks, deep learning, support vector machines, these things, they often have their linear model aspects. So this is where then the linear model also branches out. Okay, there things like, for example, MANOVA, so multivariate analysis of variance, is in this conceptualization the same thing. So it's not really the general linear model, so I don't list it here, and I think we will also not discuss it in the winter term, but it's closely related. Yeah, so there are things that are closely related to the general linear model, and if you know about the general linear model, then it's much easier to understand these other techniques. Good. So this is the approach we take here, and how this works out and why this is the case. This is actually, you have to be quite patient, because this is kind of at the end of the course, we will basically discuss how one can formulate the GLM in a specific way so that you recover things like t-test, Anova with interaction, Anova, and so on. Simple linear regression we used as an example quite earlier. Yeah. So, but please be patient. So I'm promising that everything can be, all these things can be part of the general linear model, but it will be 2018 until you actually see that, unless you read the whole script from the last year before that. Good. Then we have to slowly get closer to the GLM. about and formulating it. So this is also an important point. So now for the next couple of weeks, actually, we will deal with the model formulation bit of the GLM. And before we do so, we need to revive one important term that you're all familiar with, namely experimental variables. And there are two types, namely dependent and independent. So who would like to explain to us what a dependent experimental variable is? I think everybody who had psychology statistics knows that. So, or both. Explain both. It's easier if you explain both at once. So, anyone? Come on, here. You are called Lena. Lena Baum. That's you, yeah. So what are independent and dependent variables? Yeah, I also always do it the wrong way around because it's a stupid nomenclature. But so tell us what. Call them. You don't call them independent or dependent, but call them what they are. Tell us what they are.
I think that independent variables are the ones you set in your experiment, and the dependent ones are the ones you measure.
Exactly, yeah, that's the thing. So the independent variables are under the control of the experimenter, and the dependent variables are then the things that you measure. Of course, that's completely counterintuitive because because the independent variables are under your control and the dependent not. So the nomenclature is horrible, but everybody, I think that was kind of one thing that you learned in psychology statistics is that there are these two kinds of things. And they were called experimental variables or whatever. And we need this distinction that you as an experimenter can manipulate something and that you then measure something. We need that fairly early on to start the formulation of the GLM. With respect to the terms of variables, we will introduce probability theory at one point and the notion of random variables. And then we give some more meaning to the term variable. So it doesn't quite match. So in terms of the just say it now, but we'll come back to that. So the independent random variable in the GLM is not a random variable, but we will talk about that. So the good thing is that somebody is harking and not using Laubbläser, but it's still annoying. So I close the window. Still hear it, but we are lucky. I mean, the other way would be this. Okay, so yeah, so experimental variables, dependent, independent variables, and now we start with the model formulation of the GLM after all this preparatory talk, and I just throw it at you for the moment, and then we look a little bit into detail, and then we start our long detour to mathematical foundations. So in principle, the GLM, and you will see this equation all the time, can be written as such, where we can, it's back again. Let's write this again. Want it in the middle. So the GLM can be written as this. And we will discuss this equation at length. So you don't. So this is kind of math as it shouldn't be taught. So there's an equation coming up, and one has to understand what's going on, but I tell you, you don't have to understand what's going on. So don't try to understand this equation at this point. We will go over and over of this equation, but I want to at least tell you the ingredients at this point. So there is something that is data, which is something that you measure, and which in terms of this dependent independent variables is the dependent variable. So that's dv. Yeah, what that really is and what's behind this y letter we will talk about. Then there's an equal sign, which is the equal sign that you are familiar from school in some way, because it's actually, well, I'm writing a probabilistic model, but anyway, it's an equal sign that you're familiar with. And then there's something called x, which is actually the independent variable, and also called design matrix. You don't need to know what a matrix is at this point. We will talk about this, but you need to know that there's an independent variable, and there is something called design matrix. There are some parameters which we will talk about, and there is an error term or something probabilistic. So now for basically for the biggest part of the next 2 weeks or so, we will talk about what I call the structural aspects of the GLM. So that's everything that is deterministic and doesn't require probability theory to understand it. So we will first talk about this bit. So that's structural, if you want. And deterministic. And then once we clarified that, and especially matrix notation, then we will talk about the probabilistic aspects, which are hidden in this little thingy here, which is actually highly important for the whole thing. So to understand what this means, we need probability theory. So this is a probabilistic aspect. Probabilistic. Yeah. So. So this just as guidance for what's coming in the next weeks, and I always will recapitulate what's going on there. So now the idea behind this model is that there is something that you know, so there's something that you specify in terms of your experiment. There's an independent variable, and there are some parameters that relate this independent variable to your dependent variable. Yeah, so there's this equation which somehow turns your independent variable to some observations, and then there's something about noise. And to basically get started a little bit in terms of what this should mean, I will now first show you something that I guess you're all familiar with, namely multiple linear regression, or at least some of you are familiar with, to introduce some notation on this y equals x beta, what this should mean. So, and also then again relate these notions of independent experimental variables and dependent random variables. So we basically zoom in a little bit on this structural aspect for now, also to motivate that we then will make quite a detour to introduce some mathematical concepts. So now I'm writing down something that you might have seen in terms of multiple linear regression. And I'm just writing this little thing here. So we are just focusing on the we are just focusing on the structural aspect, so there will be no noise. But we're also introducing some notation already. So for who has seen an equation roughly like that? Well, that's more the majority. So this is something that I would call multiple linear regression. Now, what is this supposed to mean? So what you, for this, for the purposes of this lecture, you should, and also later on, if there's like a symbol with a little subscript, usually this is a scalar. So what you should think what this means is, for example, that yi is a number, let's say 9, yeah, and these xi1, beta 1, xi2, beta 2, and xip, beta p's, these are all numbers, yeah. So there is this I, and this I indexes the different y's. So I, for example, goes from 1 to 10, and I will call this number always n. Yeah, so that's my n here. Looks like a U, but that's an n. There are, so what this means is if this I can take on multiple numbers, that there are more of these yi's. Yeah? So you can think there's one yi, namely, let's call that y1, that is 9. And what this equation wants to say is that that this yi equals this sum here. So there are plus signs, so you add something, and there are dot signs, or basically nothing, so you multiply something. So to maybe give a concrete example now is that if, maybe I write the whole thing very clearly. So for example, if now our I equals 1, let's make it simple, then and our p equals, so that's the p here, our p equals 3, then we can write this as y1 equals x1 1 beta 1 plus x1 2 beta 2 plus x1 3 beta 3. And so the only thing that has changed is that we gave a certain meaning to p now, and thus are left with this equation. And now we can make it really concrete in terms of numbers. So again, let's say as an example that y1 is 9. Then we could, for example, have x11 being, let's say 1 times beta 1 being 2. So we have 9 equals at this point 2, which is not true. So we need to add at least 7. So now we need to, not at least, but we need to add exactly 7 to make an equality. So let's have, I don't know, 2 times 5. So then we have 10 plus 2 is 12. So to get to 9, we have to subtract something again. So we have to subtract 3. So then let's have minus 1 times 3. Yeah, is that correct? I always make mistakes in these kind of things. So 1 times 2 is 2, plus 10 minus 3 is 9. So what does this have to do with our independent and dependent variable? The thing is that what this is trying to do is to relate some things that an experimenter does know, namely values of independent variables, which are these x's here. So this one the experimenter knows, this one the experimenter knows, and this one the experimenter knows, for a given data point y1. So you can see that the independent variable has two indices. So one is that it refers to this y1. So it's always 1, 1, 1. So it refers to y1. But there are three different axes. So there are three, in this case, three independent variables. And they can take on numerical values. So you see that x11 is 1, x12 is 2, and x13 is -1. So these, in terms of what you know from undergrad statistics, so independent variables, they take on numbers. They can take on values, so numbers, in this case 1, 2, and -1. But they take on specific numbers for specific data points. And then we have, in addition, I start to like these different colors. That was never possible on the board, or at least I didn't want to have all colorful hands. Then there are things that now somehow relate the independent variable to the dependent variable. So first let's make clear that the dependent variable, let's do this now very pedagogical. So that's now that's now IV. It doesn't work, my color scheme. So the axis, these are the independent variables. This is the dependent variable, but it's a number. And then there are things that relate the independent variable to the dependent variable, namely these parameters, beta, beta 1, beta 2, and beta 3. And as you can see, the beta parameters, they only have one index, and they don't don't change with the dependent variable index. Yeah? So this is kind of a fairly specific example. So maybe let's of the GLM. So maybe let's the one thing that I want to make and convey here is not so much the mathematics, but what you know and what you don't know when you are an experimenter. So what you know, so the axes. The axes are the independent variable. Do you know that before you acquire the data, or don't you know it? You know that, yeah. Because you said it. There's something called correlation, where you sometimes also sample something that you might call the independent variable, but in general, you know it, and especially in the GLM, because it's not a random variable, you know it. So the independent variable is known before you know the data. Then, of course, you sample data. The dependent variable is known once you sample it. Yeah. So that's observed, let's say. So you can observe the data. And then you have these parameters, and these parameters are unknown before you observe the data. And once you have observed the data, like I said, you can do something called model estimation. So you can determine a guess for these parameters, but they are not something that you measure, so they will remain unknown. That's something to get used to, and we will come back to it, especially when we do probabilistic models. So for the moment, the parameters are something that you can determine based on your model and based on your data, and you will get a good idea, or maybe a better idea, depending on how the characteristics of your model and your data are, about the true values of these parameters. But we have to come back to that. So now, what I try to establish here, is that with the GLM, we somehow have kind of we use a formal language. So you see there are YIs and equations and so on. that this formal language is meant to describe some numbers, and that we actually are interested in many numbers. So we have i's that may take on large values n here. So we need to, and this may be different from your undergrad statistics, because in undergrad statistics it's like, oh, look, there's an equation and now it should be clear. We try to be more mathematical, so we will basically next discuss foundations that you need to understand this whole thing, and also to write this more concisely, to relate, for example, this equation here clearly to this general equation. So we next delve into the mathematics of things. So in terms of maybe before I ask for questions, as a concrete example, this is one, on the one hand, it's kind of, from my perspective, it doesn't make that much sense to talk about concrete examples here, because it's a general and fairly basic mathematical equation. But you can also think that this is something very concrete, and what you need to try to do is always to come up with examples yourself to understand things. But I can also give you one example here. So, for example, this y1 is so this 9 here is something that you measured at a specific location in the brain. Yeah. So let's say that this is this y1, this 9 here is the value of the bold signal in primary visual cortex. So then what the GLM wants to say is that this value of the bold signal can be described as a sum of things, namely some experimental predictor, some independent variable that for this specific data point here takes on basically has three different things that vary. For example, it could be the contrast of of a visual stimulus, the orientation of a visual stimulus, although that would be a little bit weird to express in terms of it's in radians, let's say, and so it's the contrast, the orientation, and let's say the color. And then the idea is that these things, so 1, 2, and -1, they are fixed for the moment when you acquired the data. And to really give you that data, they have to be scaled by some parameters that are maybe dependent on the whole measurement process and the neural system that then gives rise to the bold data. Yeah? So that's one example, but you can come up with other examples. This could be some IQ value. Well, that would be fairly low. But it could be a shoe size that you try to explain with three other, so a US shoe size, I guess, that you try to explain with three other measurements that you made. For example, I don't know, the gender here, coded in 0, 1. What else? I don't know, the weight, and what else for shoe size? Length of the arm is -1. Doesn't make any sense, but so that's the general logic, yeah. And I think this is where I stop explaining this. So because it mainly serves as a motivation for now, and especially then next session, start looking into some mathematics. And then once we have introduced the formal language, it will be much easier for me to talk about all of this, because right now I'm struggling a little bit to talk about this. But before we close, of course, questions. Are there questions at this point, maybe about this little equation here that we discussed, the notion of independent variables, something you want to know about this, anything that is on your mind right now, something that confused you? Was everything perfectly clear? If not, ask yourself what was not clear and try to put this into words and utter it as a question. Yeah.
I guess what's not clear to me is that how you can put variables in an equation together that have nothing to do with each other. So is it the parameters that will give them some kind of like overall relation?
Yeah, that's a good point, actually. So the question is, why do these things that have nothing to do with each other? So that's actually the essential part in model formulation, that you essentially postulate that they have something to do with one another. But then, and hopefully this also will get clear at one point, is that even if you postulate that, for example, this x11, which is here 1, has to do something with that, because you postulate it because it's in your model. It can be, if the model setup is working fine, that you actually get as a parameter a 0, which basically says whatever this value of the x1 or this xi1 variable is, it doesn't matter. So then, because it doesn't contribute to the value of the dependent variable, so that means then that actually the model setup tells you that although you assumed there is a relationship, actually the data together with the model tell you, no, doesn't look like it. Yeah. So you can put things into this equation together, but the framework of the GLM then also allows you to infer that things were not related.
Okay.
Diane, we are just being shut in. That's my Twin Peaks issue these days. And it feels almost like talking into this machine. Anyway, good. Yeah, but very important question, of course. So you formulate some relationship, but it doesn't need to be necessarily there, and the framework allows you to test whether it's actually there.
Okay.
Other questions, yeah.
In this course, are we going to learn how to do parameter setting, or are we going to be provided in practice?
Yeah, so if I understand your question correctly, so you asked about are we going to learn how to do parameter setting? If you refer to obtaining parameters, so estimating parameters, yes. So we will talk about the principle of ordinary least squares slash maximum likelihood. From my perspective, more maximum likelihood, which is actually a method to, once you formulated a model, to obtain parameters. And this little equation I wrote in the first lecture next to model estimation is actually the equation that you can use to set these parameters. Yeah, let's keep it at that for now. Other questions?
In this last equation, just to be clear, how could you explain the I and the P? Could you say that I is the number of participants you have, or the number of elements?
Yeah.
And then P is the number of variables?
Exactly. Yeah, very good question. I didn't talk about that. So I is actually the index for the data points, and the number of data points would be n. Now data points can be many things. In terms of fMRI data, that would, for example, be the number of images you make of the brain. In terms of where you have different participants, it can be the number of participants, it can be the number of rats that you use. So it's the number of data points, really. And data points, because we are dealing with a univariate approach, each data point is always one single scalar number. Yeah? And P, also, as you said, that's the number of parameters, or the number which, because for each parameter you have an independent variable, it's also the number of independent variables. Yeah, and this will be consistent over the winter term, that the number of data points is always n and the number of parameters is always p. So we will see that again and again. Yeah. Other questions? I think there were no questions. No. Okay, so then we stop here. So this was now a first intro. You will not see, maybe I shouldn't do this all the time, because then if you watch the video, you would get really dizzy. We we've introduced a little bit about the GLM, but we will then next talk about some mathematical foundations like sets of numbers, so that you are familiar with my writing of this GLM, and then especially matrix calculus, because as you've seen already here, the way we want to formulate this is in terms of matrices. I need to introduce you to matrices. Yeah, good. So then let's stop here, and I see you again next Monday at 10 o'clock.